Classification of semiconductors. Semiconductors are classified into two types. One is intrinsic semiconductor and another one is extrinsic semiconductor. Here that intrinsic semiconductors are pure semiconductors and extrinsic semiconductors are impure semiconductors. That is the intrinsic semiconductor added with impurity are called as extrinsic semiconductor. Now let me say in detail about intrinsic semiconductors. It is an extremely pure form of a semiconductor and it is known as intrinsic semiconductor. And here this intrinsic semiconductors, even at a room temperature, it creates electron hole pairs. When we apply an external electric field across an intrinsic semiconductor, then there is a current conduction takes place by two processes. One is by free electrons and another one is by holes. When these free electrons are produced due to breaking up of some covalent bonds by thermal energy. At the same time, these holes are created in the covalent bonds. When these free electrons are produced by breaking the covalent bond due to that thermal energy, simultaneously there is a holes are created in that covalent bonds. So look at this diagram. This is an silicon. Silicon is taken as a semiconducting material here, and these are its valence bands, and one atom is coupled with that, is closely coupled with that another atom. That is, this is the called covalent bond. That is a bondage of electron from that one atom which is coupled to the electron of that another atom. This bondage is called as covalent bond. This will get breakup when there is a this material is subjected to an thermal energy, or when we apply an external electric field, then in this semiconductor the current conduction takes place by this holes. This is a free electrons, and when this free electrons moves away from this covalent bond due to that thermal energy, then there is a hole is created in that. So that the electron hole is created. That one is constitutes the current in semiconductors. So therefore the total current inside the semiconductor is sum of both that free electrons, the current due to free electron and holes. At room temperature, the semiconductors are as little current conduction capability. Now we can see in detail the conduction in intrinsic semiconductors. Look at this diagram. We will take this one as that a semiconducting material in which just consider it has two ends. One is left side end is A and the right side of the end is B, and this semiconductor material is connected with a power supply. There is an external DC power supply is connected to this semiconducting material. That is here that end A is connected to the positive of the battery and the end B is connected to the negative of the battery. So here in this diagram, in the external wires, the electron current is mentioned. That is the current in that external wires are due to electrons. But actually, in practical cases, the current conduction in external wires are conventional current direction. That is the current direction which is opposite to that of electron movement. If the electron is moves from that left to right, the conventional current direction is right to left. That is usually a conventional current direction is positive of the battery to the negative of the battery. But here to understand that the current conduction capability of semiconductors, here that the electron current direction is shown in this figure. Okay, when this electrons moves from one place to another place, it constitutes the current. Then what about the holes under this situation, under this condition? Here, these holes are positively charged ions, and that one is moves towards the negative of the supply, negative terminal of the battery supply. Since this electrons are moves towards the positive of the supply, and since it is an opposite charges are attracted each other, based on that principle, that is here that holes are attracted towards the negative of the battery. As this the holes reaches the negative terminal B, this holes which reaches the negative terminal B, and that electrons are enters into the semiconductor near the terminal B, and both are combined. That is, these electrons are combined with these holes, both are combined together and cancel each other. If both this electron hole combines and both are cancel each other. At the same time, here some of the loosely electrons which are present in the near that terminal A are attracted away from their atom, and that electrons are moved towards the positive terminal of the battery. So that one is creates new holes near the terminal. If these electrons which are nearer, loosely held electrons which are nearer to the terminal A are moved towards the positive. If these electrons are moved away from this end A, then automatically then there will be a holes, that is a empty space. Electrons is moved means that is the empty space that are all called as holes. Holes are created near that terminal A, and that is it again drifts towards the that created holes are drifts towards the terminal B. Now, based on this concept, we can define a drift current. That is the current which is produced due to drifting of free electrons. That is a drift means here it is a movement of free electrons from that one place to the another place. It's called as a drift current. And velocity with which the electrons drift from is called as a drift velocity. It's very important. Drift velocity is velocity with which these electrons drift. Drifting means it is a movement of electrons, free electrons from that one place to that another place. How fast? That is the speed. Velocity means here is speed. What is the speed at which the electrons are moved from one place to another place? That is called as a drift velocity. Now the another term, recombination. What is recombination? Recombination means merging of free electrons with holes. That is, if the electron hole combines each other, then that combination is called as a recombination process. If this recombination process, the rate of recombination increases. If the electrons are combined with the holes, then both are cancel each other, then the number of charge carriers decreases. Whenever a recombination rate is increases, recombination means electrons is combined with the holes. If this combination takes place, then both are cancel each other, so that the number of charge carriers which are present in that material is decreases. So note this, if the recombination rate increases, number of charge carriers decreases. If the number of charge carriers in a material is decreases, then we can say that one is decreases the current conduction. So it decreases as a result of this, the current conduction in that material is decreases. So next, the next term is mean lifetime of a charge carrier. What is the lifetime of a charge carrier in that semiconducting material? It can be defined as there is a time gap between a thermally generated charge carriers and the time at which the recombination occurs. A recombination takes place. The gap between these two, thermally generated means it generates a more number of charge carriers. Recombination means free electrons is combines with the holes. So what is the gap, a time gap between these two? That is called as a lifetime. In between only the charge carrier is live in that material, So that is called as a mean lifetime of a charge carrier. The next one is, we can move on to that, extrinsic semiconductors. What are extrinsic semiconductors? It is that we know already we have discussed about that intrinsic semiconductor. That intrinsic semiconductors are that pure form of the semiconductors. That is, since that are the pure form of the semiconductor, pure form intrinsic semiconductors are the pure, and that are all not that much useful or used in electronic devices because of its current conducting properties, because it has that very less current conducting properties. So to make it that semiconducting materials much more useful in electronic devices, certainly it must be altered. Which one? That intrinsic semiconductor must be altered. to increase the current conducting property of that semiconducting material. How to alter? Alter means it's nothing but adding of some amount of impurities. When we add some suitable small amount of impurity with that intrinsic semiconductor, then that becomes an extrinsic semiconductor. So extrinsic semiconductor means intrinsic semiconductor added with some small amount of suitable impurity. That are all called as extrinsic semiconductors. Now, the process of adding that impurity to the intrinsic semiconductors so as to make it as extrinsic semiconductor, that process is called doping here. So doping can be defined as a process of adding impurities to the semiconductor, or we can say injection of impurities to a semiconductor. Both are one and same. Injection of impurities to a semiconductor or adding impurities to a semiconductor is known as a process doping. What's the purpose? Why we are adding that impurity to that intrinsic semiconductors? Because to increase the number of free electrons or holes in the semiconductor. This addition of this impurity increases, that is a suitable impurity, depending upon the type of impurity which is added. Either it increases the free electrons or increases the holes. Say we will see that what is the type of impurity which we are going to add and how it creates that free electrons or holes. If we add a pentavalent impurity, that is if we add a pentavalent impurity means pentavalent means that is a penta means here it is a 5. So it has that 5 valence electrons. That's why it is called as a pentavalent impurity. That is it has a 5 valence electron. If this one is added with that intrinsic semiconductor, then it can produce a large number of free electrons in the semiconductor. That is even a small amount of addition of this impurity can produce a large number of free electrons. Suppose if we add a trivalent impurity. Trivalent means, tri means here it's a 3. It has a 3 valence electrons in its outermost orbit. If it is added, then that one creates a large number of free holes in the semiconductors. So pentavalent is 5 valence electrons, and it increases the large number of free electrons. If it is a trivalent impurity, that has the 3 valence electrons, and that one increases a large number of, or it creates a large number of holes in the semiconductor. So it's clear that from this discussion, depending upon the impurity which is added to the intrinsic semiconductor, it becomes an eccentric semiconductor. And based on that type of impurity added, we can classify this extrinsic semiconductors are into 2 types. One is N-type semiconductor and another one is P-type semiconductors. Now you can see in detail about that N-type semiconductor and then next P-type semiconductor. What is an N-type semiconductor? When a small amount of pentavalent impurity is added to a pure semiconductor, then it is known as N-type semiconductor. This addition of pentavalent impurities provides a large number of free electrons in the semiconductor. If you add a pentavalent impurity, it provides or it produces a large number of free electrons. The examples of pentavalent impurities, that is the impurity which has 5 valence electrons, are arsenic and antimony. These are all its atomic number 33 and its antimony atomic number is 51. Just consider this diagram. Look at here. This is the arsenic. That is, arsenic is added here. Arsenic is the impurity which is added with that germanium. Consider this germanium has 4 valence electrons. Note, the impurities which produce N-type semiconductors are known as donor impurities. Why? Because this addition of pentavalent impurity produces a number of conduction band electrons, that is free electrons in the conduction band. Total there are 4 free electrons, valence electrons of pentavalent atom. It forms a covalent bonds with 4 neighboring germanium atoms. Look at here, this 4 valence electrons in the impurities are bonded with the germanium, and it leaves one electron without bondage. That one is acts as a free electron here. So fifth one is left over, valence electron of the pentavalent atom is cannot be accommodated in the valence band, and that one is travels to the conduction band. That free electron is travels to the conduction band. Okay, look at this. Conductivity in n-type semiconductor. The current conduction in an n-type semiconductor is by free electrons, that is negative charges, and hence it is called as n-type conductivity. Here, this is the n-type semiconductor is connected with the power supply. Positive is connected to the one end, and negative is of the power supply is connected to the another end. When the potential difference is applied to the n-type semiconductor, this free electrons will be directed towards the positive terminal, that is attracted towards the positive terminal. Then that one is constitutes a current, electric current. As this current flows through the semiconductor is by free electrons, which are of negative charge carriers, this conductivity is called negative conductivity or n-type conductivity. In case of a p-type semiconductor, look at here, a gallium, a impurity gallium is added here. Consider a germanium which has a 4 valence electrons. This addition of trivalent impurity, that is a gallium, it provides a or it produces a large number of holes in the semiconductor. That is, example for trivalent impurities are, trivalent means 3 valence electrons. Here it is a gallium. Gallium is, its atomic number is 31, and indium is its atomic number 49. Since this gallium has 3 valence electrons in its orbit, these 3 electrons are bonded with the germanium, and germanium has, since germanium has the 4th valence electron, there is no electron is available in this gallium, and that space is empty here. So it produces a p-type semiconductor, and that impurities are acceptor impurities because the holes created can accept the electrons. That's why this impurity is called as acceptor impurities. Consider 4 valence electrons, trivalent impurities added, it creates a large number of holes. Gallium is a trivalent one, since it has a 3 valence electrons. Here the 4th bond is incomplete one, then there is a shortage of 1 electron. This missing electron is called hole. Note, a small amount of gallium can provide millions of holes. Then now, energy band description of p-type semiconductor. Look at that energy band diagram. This addition of trivalent impurity has produces a large number of holes. Only a few conduction band electrons are available due to thermal energy at room temperature. But the holes far outnumber the conduction band electrons. It is due to predominance of holes over the free electrons, that it is a called p-type semiconductor. Now the conductivity in p-type semiconductor, consider there is a p-type semiconductor, a power supply, a potential difference is applied across the p-type semiconductor. Here the current conduction is p-type semiconductor is by holes, the movement of holes, that is the positive charges, and is called p-type conductivity. When potential difference is applied to the p-type semiconductor, these holes are shifted from one covalent bond to another. Here, look at here, these holes are attracted towards the negative of the supply. As these holes are positively charged, they are directed towards the negative terminal, and it constitutes a hole current. Note, in p-type conductivity, valence electrons are moved from one covalent bond to another. Charge on p-type and n-type semiconductors. Majority and minority charge carriers in p-type and n-type. This n-type material has a large number of free electrons, but p-type material has large number of holes. At room temperature, some of the covalent bonds breaks and thus releases the equal number of free electrons and holes. In n-type material, large number of free electrons are generated and it has a small number of holes. In case of a n-type, free electrons in this case are called as majority charge carriers, since the majority portion of the current in the n-type material is by the flow of free electrons. So here the majority charge carriers are electrons and minority charge carriers are holes. Holes are the minority charge carriers. Similarly, p-type material as a holes outnumbers the free electrons. Holes are majority carriers and free electrons are the minority carriers. Look at this diagram. Here majority charge carriers are holes and minority charge carriers are electrons. Now we can go for this law of electrical neutrality. Law of electrical neutrality. That is, this law states that in any atom, that the number of positive charged particles is equal to the total number of negative charged particles. That is, it maintains a electrically neutral condition in an atom. That is, the number of positive charged particles is equal to the total number of negative charged particles. It can be given in the form of an expression that here N is that concentration of electrons and P is that concentration of holes. Here free electrons, and it is a concentration of the holes. Na is a concentration of acceptor atom and Nd is the concentration of donor atoms. So both are equal in amount. So that one maintains a electrically neutral condition. Based on this, a law of mass action for extrinsic semiconductors. Now we are going to apply a law of mass action for the extrinsic semiconductor. This law of mass action is given by, here we can take a Pn is the concentration of the holes in n-type. Pn is the concentration of hole in n-type and Nn is the concentration of free electrons in n-type. Like that, here Nd is the concentration of the donor atoms and Na is the concentration of acceptor atoms. And Ni is that intrinsic concentration. Intrinsic charge carrier concentration is, here it is a Ni. Based on this, we can go that in n-type semiconductor, we can write that is a concentration of electrons in n-type material and the product of a product with that, if it is multiplied with that, concentration of holes in n-type material. It's a concentration of electrons in n-type and concentration of holes in n-type. That is equal to Ni square, because the Nn is nothing but a intrinsic concentration Ni and Pn is nothing but another Ni. So both get multiplied, it becomes a square, Ni square. If we assume that is the concentration of free electrons in n-type is approximately equal to the concentration of the donor atoms. Concentration of the donor atoms both are approximately equal. Then we can write instead of Nn, that is a concentration of electrons in n-type, can be replaced with that donor atoms. So Nd, Pn is that the concentration of holes in p-type, that is equal to Ni square. Then from that above equation we can write the concentration of holes in n-type is equal to Ni square by Nd. In case of a p-type semiconductor, similarly Np, what is Np? It is a concentration of holes in concentration of free electrons in p-type and concentration of holes in p-type. So that is equal to Ni square once again. Here it is a Nn, Pn, here is a Np and Pp. Similarly, if we replace, that is a concentration of holes in p-type is approximately equal to Na. That is a concentration of acceptor atom. Then we can write NpNa. Just substitute that one in place of Np here. Na is, that is in place of Pp, we can substitute Na. We can write it as Ni square. Now this Np can be written from this above equation Ni square by Na. So from that above discussion, we can write the conductivity in extrinsic semiconductor is given by the conductivity equation. Sigma is the conductivity, that is equal to N, that is the concentration of free electrons, into mu n is nothing but here it is a mobility of free electrons, and mu p is that mobility of holes. Even though in the electrical neutral condition the number of free electrons and holes are maybe equal, but the mobility of that electron and holes is entirely different. The mobility of electron is differs from that mobility of holes. So n mu n plus p mu p, that into E, it can be expressed in terms of that is a mho per meter. See, if it is taken for that n-type semiconductor, the conductivity equation for n-type semiconductor, then we have to take since the n-type semiconductor, electrons are that majority charge carriers. So assume that by taking n is very much greater than p, that is the concentration of the free electrons in n-type is very much greater than the p concentration of the holes. Hence we can write the conductivity of n-type semiconductor is n mu n into E. From that we can write n is nothing but an nd, can be approximately equal to nd, concentration of the donor atoms, mu n E, mho per meter. Similarly, in p-type semiconductor, the majority charge carriers are holes. Since it's a p-type semiconductor, majority charge carriers are holes and the electrons are the minority charge carriers. So it's clear P is very much greater than N. That is the concentration of holes is very much greater than N. That is the concentration of electrons in case of a p-type semiconductor. Hence, we can write the conductivity equation for that p-type semiconductor as sigma p is equal to pp mu p into E. We know that here pp is nothing but it is a concentration of acceptor impurities, that is a Na mu p into E. This is the conductivity equation for n-type and p-type semiconductor. From this, we can write like the definition for that diffusion current and the expression. The current due to the transport of the charge carriers in a semiconductor due to a non-uniform concentration of the charged particles is called diffusion current. Already we have discussed about the drift current. Here it is a diffusion current. It is a non-uniform concentration of the charged particles. Transportation is called diffusion current. Consider a p-type semiconductor in which there is a non-uniform concentration of the charged particles. Here, that is the charged particles, that is one is taken with the distance. Depending upon the distance, the charged particle, the charge carrier concentration is entirely different. It varies. Like at x1, at a distance x1, the charge carrier concentration is P1, and at a distance x2, concentration is P2. It is taken from this diagram. By taking a p-type semiconductor, these are the holes, the concentration of the holes at various distances. X1, the concentration of holes at P1, and at x2, the concentration is varies, it is a P2. So the current density of the p-type is given by, that is a current density J for p-type semiconductor, that is directly proportional to that dp by dx. That is, we are going to differentiate that is the concentration of the charge carriers in that, the concentration of that holes in the p-type semiconductor with respect to the distance x. There is a Jp with the constant of proportionality minus q. A charge into dp can be expressed as dp by dx amps per meter square. With this, we can write the current density because of drift is given by Gp is equal to pp mu p E into electric field E. Capital E is electric field, small E is electron, that is electron charge. Then for that n-type semiconductor, this is for the current density of the p-type semiconductor. Current density of n-type semiconductor is n mu n E into capital E, that is electric field. So the total current density in the sum of the drift current and diffusion current, that is it is sum of the total current density in any semiconductor material is due to both drift and diffusion current densities. In case of a n-type semiconductor, Jn is, that is this is the current due to that drift and this is due to a diffusion current density. So both are added together. Like that p-type semiconductor, this is the current due to that drift current, and there is a diffusion current. So Einstein relationship gives the relationship between that mobility and the diffusion constants. That one is dP by mu b is equal to dN by mu n, that is equal to Vt. Here Vt is that voltage equivalent of the temperature, and it can be given by the expression kT by Q, where K is that Boltzmann constant, we know very well. It is of 8.62 in 10 power minus 5 electron volt per Kelvin, and T is the temperature in Kelvin, and Q is the charge of an electron. And at room temperature, we can express the Vt as 26 millivolt. If you take a Vt is 26 millivolt at room temperature, we can write the charge Q is 1.602 in 10 power minus 90, and T is the 300 Kelvin. So Vt at any given temperature is given by Vt is equal to T by 11,600. Now we can go for this open circuited PN junction. Now let me start with that. How to form PN junction? How to form a PN junction? When a p-type semiconductor is suitable joined to the n-type semiconductor, then that contact surface is called PN junction. Most of the semiconductor devices contains at least one or minimum one or more than one PN junctions. This PN junction has a great importance because of it is control element for semiconductor device. It is a control element for the semiconductor devices. At the instant of PN junction formation, this free electrons near the junction in N region begins to diffuse across the junction into the P region. That is, once that PN junction is formed, while forming that PN junction, electrons near the junction are diffuses across the junction and moves towards the P region, where they combine with the holes near the junction. Then the donor ion represented by positive sign, because of after impurity atom donates an electron, it becomes a positive ion. So that acceptor ion represented by negative sign, because after impurity accepts an electron, it becomes negative ion. So donor are represented by positive sign, acceptors are represented by negative sign. Consider this diagram. Here, this is while forming this junction, that is the electrons in the N region is drifts towards that P junction, and holes in the P region is drifts towards that N junction, and it forms a depletion region. Result of drifting of electrons from that N to P and holes from P to N. First, the electrons is drift from N to P. So here, this N region loses the free electrons, and it gives a space of holes. So that holes occupies that space. This creates a positive charges near the junction. As these electrons are moves across the junction, the P region loses a holes as the electrons and holes combine. Result, the layer of negative charges near the junction. These two layers of positive and negative charges near this junction forms a depletion region, or it is called as depletion layer. This dotted line is called as this is the junction. Near the junction there is a negatively charged ions, here it's a positive charged ions, so that this forms a depletion region. This is called depletion region. Since the region of the junction is depleted of mobile charges, there is once there's a depletion region is formed, it depletes the mobile charges. Furthermore, no free electrons, the electrons from the N region and holes from the P region can move towards this junction, can cross over the junction. Okay, so that the depleted of mobile charges in the junction. That's why this region is called as depletion region, and also it is called as space charge region or transition region. Note that depletion near the junction, the region is depleted. That is, depleted means it is emptied of charge carriers. Note here depletion layer is formed very quickly and is very thin compared to the N region and P region. Look at here. This depletion region it's very thin compared to the N region and P region. Once this p-n junction is formed and depletion layer is created, the diffusion of free electrons stops. Free electrons can't able to diffuse this junction. Or we can say that depletion region acts as a barrier to the further movement of free electrons across this junction. It forms a barrier to the movement of free electrons from N region to the P region, or holes from P region to the N region. This positive and negative charges near the junction, that is the depletion layer, set up an electric field. This forms an electric field, and this electric field acts as a barrier to the free electrons in the N region. There exists a potential difference across the depletion layer. So it is a negative charge, positive charge. So there is a potential difference across a depletion layer, and this one is called barrier potential, and it is mentioned here V0. Look at this. Here there is an acceptor ion and donor ions are there. This is the junction, and now we can say we can discuss about the charge density and then electric field intensity. The general shape of the charge density rho s depends upon how the diode is doped. Okay. Since the region of the junction is depleted of mobile charges, it is called depletion or space charge region. That thickness of the charge region, that's the space charge region, is in the order of wavelength of visible light. That is 0.5 micron. That is equal to 0.5 micrometer. Space charge region thickness. The density rho is 0 at the junction. Look at here. The density is 0. Charge density is 0, exactly 0 at the junction. And it is positive to the right and negative to the left of the junction. Positive to the right of the junction and negative to the left of the junction. And then the electric field intensity is negative. Always it is negative. The field intensity curve is proportional to the integral of the charge density curve. If you integrate this, we can get this electric field intensity. So it is derived from Poisson equation, that is d square v by dx square is equal to minus rho by epsilon, where epsilon is the permittivity. If we integrate that above equation and remembering that epsilon is equal to minus dv by dx, it gives that electric field intensity as integral x naught to xn. This is the distance, rho by epsilon into dx. Now open circuited p-n junction means, consider the p-n junction diode or a p-n junction. If no voltage is applied to the junction, then the diffusion of holes and the electrons must eventually cease. That is, a ceased means it is a stopped. So under this condition, it forms a thermal equilibrium. Under the thermal equilibrium, it forms a depletion region. That is, here as the negative ions, as the positive ions, the depletion region. The p-n junction and a thermal equilibrium is 1. The junction is x is equal to 0. Junction. That is the distance at the junction starts from junction. It is x is equal to 0. The direction of the induced electric field will cause resulting force to repel the diffusion of holes from the p region and the diffusion of electrons from the n region. This electric field which is formed near the depletion region creates a force. Then thermal equilibrium occurs when the force is produced by electric field and force produced by the density gradient exactly balance. That is called thermal equilibrium. This positively charged region and negatively charged region comprises a space charge region. Already we have discussed. Since here there is no mobile electrons or holes, and it possesses a barrier potential of V naught. Because of this electric field in the space charge region, there is a potential difference across that region. Then that one is called as a barrier potential or built-in potential barrier. This barrier potential is given by that equation VBI is equal to KT by E ln NA ND by NI square. That can be written as VT ln NA ND by NI square, where this VT is the KT by E and K is the Boltzmann constant, T is the absolute temperature, E is the magnitude of electronic charge, and NA and ND are the net acceptor and donor concentrations in P and N regions, where VT is a thermal voltage. Approximately at room temperature, the thermal voltage is 0.026 volt and T is equal to 300 Kelvin. This potential difference across the depletion layer is called barrier potential and is represented as V naught. Already we have discussed. We have seen that it is barrier potential is represented in terms of V naught here. That one, this is the depletion region and its potential is V naught. This is the potential V naught. The potential difference between this negatively charged ion and positively charged ion is known as V naught. This potential barrier potential of a PN junction depends on several factors. They are type of a semiconductor material. This barrier potential V naught S depends upon several factors. One of the factors is type of semiconductor material, amount of the doping, and temperature. The typical barrier potentials is approximately 0.7 volt for silicon and 0.3 volt for germanium. Yes, note down this. It is very important throughout the study of electronic devices and circuits. We have to remember this. Barrier potential is 0.7 volt for silicon and 0.3 volt for germanium.